want to do tonight is go back over the fundamental form of thin film structures, which is not the transformer, which is the transformer takes impedances and matches them to air, notably anti-reflection coating and beam splitters, okay, are step down or step up transformers, okay? The second most important structure in thin films is the quarter wave stack and its variations. And you're going to run into this continually in your work in photonics. It also means color filters, spectral separation filters, heat filters, most of the specialized units which are transform the energy from one spectrum size to another are based on the quarter wave stack. The third and last structure in thin films is the solid state Fabry-Perot interferometer, or the solid state interference filter, which you will all use rapidly in the lab. You pick them up and you look through them and says, oh, it's a filter. It'll put one wavelength through at a certain bandwidth, etc., which you will be using forever in photonics. Okay. Now we'll do with that a little bit next lecture, but the basic thing that we should talk about now is, in fact, the quarter wave stack. Now, the trouble with this is that we're dealing with 19, 20, 30, 50 layers. It's huge, okay? And to get a handle on what is going on there, we can't use the vector method because it fails with so many vectors running around. It's very cumbersome to do it. To do it hard-nosed with the computer, yeah, we can do that now, but I want to go back over the original work that was done in the modification of the quarter wave stack. And that means how does one look at this stack? Now, over on the left, I have a filter project. Let's modify the filter. Now this is the reflectance of the stack. Here is a quarter wave stack, and it's made of two materials. Notice that all of these are quarter wave, and it's high, low. Oh, I have them. This is modified. High, low, stack 01. Did I make the stack 01? Yeah. Okay. No, it's all quarter waves. That's correct. Okay. And each of them is a quarter wave. High, low, high, low, high, low, high, low, high, low, high, low, high, low. Okay. Now it ends up with a high, low. And if I look at this filter, under filter, the stack formula, you see I wrote it as high, low, high, low, high, low, high, low, high, low, high, low, all of that. Whoopie-doo, okay? You all saw that. Now, I tried to write it a different way, but in other words, put it down as high, low to the power. We'll show you that in a minute, okay? Now, and here is the quarter wave stack, and let me show you for a moment the oh, it went back to the other part. Oh, here's the quarter wave. He calls it the reflectivity of multi-layers with periodic structures. Periodic mean it's high, low, high, low, high, low, high, low. Okay? Periodic structures. And here you see the basic stack, low, high, low, high, low, high, air, or it can be written as low, high to the fourth air, which we will look at in a minute in terms of using that in here. And the typical quarter wave stack as you've seen from the, this is 8 layers, the 7, I gave you an 8-layer stack to look at the various impedances, okay? And to look at the reflectivity coming out of it. Now, when you look at this, remember, over here, we are looking as a function of lambda 0 over lambda, so that we don't have to specify where this structure is in the spectrum. We're saying that it doesn't matter, just like the quarter wave layer is a symmetrical V like this, one quarter wave. 2 quarter waves is like this, okay, symmetrical around G is equal to 1. So this is really phase, okay? Because the phase is 90 degrees times G, lambda 0 over lambda, times FR times the number of quarter waves. That's the phase. So this is phase. Now, phase is linear on both sides of the lambda versus lambda 0. So it's 1 over lambda function. When we look at wavelength, it pulls this out and compresses this. So here you see the same stack, which would be symmetrical in phase. You'll notice these wiggles, this wiggle and this wiggle, are this wiggle and this wiggle, okay? The same on either side of the phase, but the 1 over lambda pushes this one longer. So it stretches the long and compresses the blue. So this is the blue side here that's get compressed, and this side gets stretched, all right? Now, so this is a quarter wave stack. Very, very nice, very nice. And you can do various calculations on how wide it is, et cetera, et cetera. But what happens is that I want you to understand that we can look at this film here, at this stack, and you don't see it on here, but if I had a trace, if I had an envelope that went all the way up to here, across, and all the way down, that's the maximum envelope, and this in here is called the high reflectance zone. This is your laser mirror, all right? With me? Found in all the lasers, typically 19 to 20 layers of 2 hard oxides, titanium dioxide and silicon dioxide, okay? So that they can withstand the vacuum inside the tube of the laser when they ignite the gases in the old days, right? Now, you notice the envelope here. This envelope encompasses all of the oscillations. So if we could calculate the envelope simply, then we would know what this stack does, because we're generally not interested in the wiggles here. We want to know how wide it is, you know, where this is, how low this is, etc. So if we could calculate the envelope here, all right, without calculating all of this, all right, well, today this calculates out in a matter of seconds, but in knowing the envelope, we can design new filters without going through playing with 24 layers and saying, hey, I want this and I want that. Get me something which does this or that based upon the envelope that encompasses the reflectivity of the entire stack. That means, quite frankly, we have to look at this quarter wave stack. Here's various types of stacks, and we'll get an overview. This stack here, this is the first period, 1. 300 comes back. So this is a a stack, which we call a basic period stack. So it's 1, 3, 5. You notice the envelope. Now, where is this? This is over here. Lambda 0 over 1, lambda G over lambda is 1/3. So if we're at 600, the peak here would be at 200 nanometers. And this last one, 5, would be all the way down below 200 nanometers, below 100 nanometers, quote unquote, if it could be there. All right. So this is the blue side, which is this side here. This is the red side here. So here we have a 1 stack, LH, 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 LH to the fourth. This one we're looking at here is 1, 2, 3, 4, LH to the fourth, okay? Okay, or we could write, well, leave that be right now. Now, what's important here is that if we could find out what this basic period was, here it's LH, here it's a different basic period. We call this the kernel. Because we're gonna, when we evaluate the kernel, we pop it like we make popcorn. And it gives me all of the goodies inside. But we know once we have this kernel, we know that it will have this kind of an envelope. This is the kind of envelope of this stack, LLH, 4 times over. That's LLH, 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 okay? With 2 different materials for low and a high. Now you notice this is now, you call it a 2-to-1 stack. 2-1 stack. It's called 2-1 here because the fundamental, you get the second order. You say, why do I want to know that? Oh my dear, you're gonna get into systems with up and down conversion. Guess what you want? Well, the main laser is 106, and the crystal, you're gonna hit a crystal inside the laser with 106, and the crystal is gonna double and produce 5300. And you want the laser to laze at both 106 and 5300 simultaneously, right? So you need high reflectivity mirrors, right, that are 99.99% simultaneously at 106 and 5300. So a 2-to-1 stack is wonderful. The 1 would be 106, 2 would divide it in half. So the second stack here would produce a reflector at 5300 at 99.9%. So here's your 2-to-1 stack, okay? And if you have a very, very higher power laser and you want a 1, 2, 3 stack, then you'll have, guess what you'll generate? 106, 5300, and then 2537. Ooh, you say, why would I be interested in that? I want to write my semiconductors. When I design semiconductors, I want to laser write the pattern of the etching for the design. Now I want those things to be very, very tight. So I want the wavelength to be in the UV. So I have here a high power laser, which will produce a lot of ultraviolet for me to burn and write those fine structures and make very fine structures for semiconductors. Okay, so this is the UV mirror system for laser writing for the semiconductor industry. Nanotechnology. You want to write with a very tight wavelength. Okay. Okay, so that is what's going on here. Now, let's go back to we're talking about.
Hey, Mark.
Yeah.
I thought they were doing E-beam.
That too. But E-beam is a lot bigger and more expensive. Here I put a laser system into a visual light screen aligner. It's called a mask aligner. And I'm off and running. Electron beam, I've got vacuum and all kinds of things to take care of. Okay. In other words, it's a technique which is used, just like this technique is being used. All right, now let us go to the fundamentals of all of this. So I'm going to go in something called partitioning. Now, follow this. We have a stack, high, low, high, low, high, low, high, low, without a last high layer. So we have high, low to the 5th air. All right. Now we could have written it as high, low as this, or the mathematically the same as this S times. Now we get the crux of the matter. the clue is if we have D is cosine gamma I sine ED, okay, then D to the S is cosine S gamma, gamma being the thickness. This is the phase, and this E is the index, quote unquote, the pseudo index of this. We call this the equivalent phase, and ED the equivalent admittance. Ooh, ooh. Well, if it's admittance, then A to 0 minus admittance, A to 0 plus admittance is the reflectivity, and the reflectivity is R a complex conjugate. Oh, so what's happening here is that we have the difference is that we have this S gamma. S gamma. Now, gamma is in degrees. S can be 10 or 15. So it's the cosine of 10 times a degree. All right. Makes it oscillate like crazy. That's this oscillation in here. Okay. The E, large resultant, is the E is the envelope under which it oscillates. So by merely looking at the kernel, just look at the HL itself, or whatever the kernel has to be, we can tell you what the structure of the film is going to be before you figure anything out. So that is S gamma, okay? So here we have the symmetrical multi-layers, high, low, high, low, high, low. All right, this is the 1-3-5 stack. All right, now let's talk to what the story was. Okay, back in the 50s, there's a Epstein who ended up being a professor, genius in Epstein and Herpin. The United States made a contract to provide the Russians for the Russian Olympic with color TV cameras. The color TV cameras had 3 cameras in them, one for red, one for green, and one for blue. And Epstein had to make filters that would separate red, green from blue. It was a very difficult process. The problem with the process is if you look at this standard stack, this would separate this is the reflectivity is very low from the blue to the beginning of the red, and then it would be high reflectivity from the red all the way out. So we need 3 filters to separate the red, the green, and then the blue comes through. But these oscillations, when they sneak through, would make the color, the human face color, the skin color, look very, very terrible. Okay? And so he was asked, would you please figure out a way to modify these filters to clean up the wiggles, get these wiggles down? Okay? And in doing so, he and Herpin, who he worked with, invented the most powerful technique for the design of multi-layer filters like this. And that's called the Herpin index. Okay? So what he did was say, hey, we all know that we add the following. Now, let me take this quarter wave stack, which you see. I'm going to say File, close this project. I'm going to say File. I'm going to open up the one which has a lambda 0 at 580, which they did an 1/8 of an inch, an 1/8 of a wave on either part of the stack. I'll show you that in a second. That is number 02. So here it is. I didn't want to waste your time with comforting tonight. Okay, 19 layers. Okay, the filter, the stack formula is high, low, high, low, high, low. Great. Okay, and if you look at the filter, you know, if we say on the project modify the filter, you'll notice this: the first layer is TiO2, the last layer is the high, but the optical thickness is 0.125. 0.25 is 1 quarter wave. quarter. Optical thickness is 0.25. That's lambda is, the multiply the index times the wavelength times the thickness in the index, and a quarter of that is this thickness. This is the metric thickness of this index, quarter wave. This is an eighth. This is a quarter, this is an eighth. So let's look at it, analyze, and we do calculate the transmission in this case at 0. Okay, so now we see, oh, look at this. We've got a good filter. In this case, it takes the 500 to 650 and transmits it and reflects everything longer than that out. All right? So what we've done is he's added a quarter wave here. So he has said that, well, this thing is now partitioned this as H on 2, LH on 2, or we're going to break this out as the machine is just written this way and partition this as H on 2, LH on 2. Okay, in other words, I'm splitting each H. You all with me, people? Okay? So we're partitioning as H2, L on 2, or L. So now, so the whole thing is H on 2, L, H on 2 to the S, where S is 6. Okay? If I can make the machine take that, I'd be happy. But what the filter program will do is it'll take this, if I put this in, and compress the half waves and make it one wave. So it'll go back to this. All right? It won't let me split this and leave it be. All right? But now what we have is method of the madness is this. All I have to do is look at the envelope of this. I don't have to do it S times, just this. Just take the kernel. So make a matrix of this form for high, low, high, and compare it with the characteristic matrix here and set cosine gamma is equal to M11 or M22, M11, and this I over E sine gamma over N of E is M12. So I know what E is from this. So M21 is E sine gamma. So this is called the equivalent optical admittance. This is the Herpin index. Okay? And so we take this and we're looking for a formula, calculate that 3. I will do this, I'll show it to you. And out pops the E, all right? So if we know this, then we know this. So we have a single layer of phase S gamma and an optical admittance of E. If I know E, I know the envelope. All right? So any structure which can be partitioned like this, knowing NL and all, we can calculate cosine gamma and E and calculate the propagator from sine a layer of equivalent thickness of the form this way. So this is the E. This is N0. What's going on with my why is it making away? So here it is. So now here is the work Epstein and Thalen, Alpha Thalen. This is 1952 and 1966. People, this is stuff which is reasonably current. All right. I will also tell you that most people in optics have never even studied this. Okay. Why is it important? I got a call. I think it was 2 years ago. A graduate of mine had joined a solar energy company. And guess what he had to do? He was working on improving the efficiency of solar cells. Solar cells in which the electricity comes from the production of photons and electrons in a thin film. And he was looking at various coatings to improve it. And so he needed to get all these references. And I gave it to him and told him where it was. At that time, the course in thin films that I gave never got to this point. All right. So Clay made it. Glad you made it, Clay. Welcome on board, Clay. Glad you made it.
Thank you.
This is all going to be in, this is all in this lecture, and the lectures in here, Clay, are all on Canvas, okay?
Excellent.
And-
Thank you, Professor.
All right, and you'll get a copy of this lecture. The next lecture, our last lecture in this subject, I'm going to give one at 6:15 on Wednesday night, the 9th, okay? If you can make it, fine. If you can't, you can always come and pick it up later, all right? That's our last lecture of this section.
Sounds good, Professor.
And I made 7 lectures out of 14 in thin films. I shouldn't have, but I did. Okay. Now, what we're talking about here is the structure. We have a structure PQP. If you can split it up into equal symmetrical trilaters, in other words, this has to be symmetrical with this. So eighth, quarter, eighth is typical, but it also be eighth, quarter, eighth, quarter. It's symmetrical. There's a reason for that. And we're not going to go, we don't use the theory, we use the method that it comes from, okay? Because with these calculators here, we can calculate it easier than trying to do it the way it's shown work here in theory. So again,
Hey, Marv.
yeah,
I don't know if the other students have this problem, but a lot of your notes are illegible.
I know. Suffer through it. I haven't retyped them, okay?
You don't type.
That's right. Can I tell you? You're right. I really should.
I mean,
Okay.
it's really it just I can't
All right.
can't anyhow.
All right. Fight later. For example, here is a 1-2 stack broken into HL, H on 2, or LH. It could be H or L in the periodic, and it depends on, it's almost a quarter wave stack. It's so easy to evaluate this that it's easier to evaluate this as a quarter wave stack than removing the eighth waves on either side. Now here is a filter guard. It's a narrow bandpass filter. You notice, people, you got HH and HH. Well, that is the Fabry-Perot spacer. So this is a mirror, this is a mirror, and this is a mirror. So this H and this H, okay, this is one cavity. This is a 2-cavity interference filter. It produces not a Lagrangian, Lambertian curve, but a square bandpass, which you will find necessary in some of your work. We'll talk about this next Wednesday. Now, here I have 1, 2, 1 again, okay, different. This is a very important one. This is a heat filter. The module is symmetrical, L, L, H, H, men. So it's a high, medium, and low 3 times over. This is the one that's used on all the architectural glass that you see on the skyscrapers, okay? It reflects the heat and transmits the visible, okay? All right. Now we can go through this process of evaluating it, all right? But I would tell you, we know what we should do, and with the optimization business here in Open Filters or the other programs, we use it to clean up the generalizations that we put through, all right? So here we have the straightforward multiplications of the 2 symmetrical, the symmetry here, and the middle layer, all right? And we do the algebra, and we end up with the product of this, of course, is another another characteristic matrix. Of that characteristic matrix, then this is what we're going to find. E is M12 is I sine gamma, okay? E is the equivalent admittance, okay? The Herpin index. We call it the Herpin index at normal incidence, okay? And at theta is equal to 0, at the angle of incidence is 0, it is the index of refraction. And you know that reflectivity is 1 minus is N0 minus y, 1 minus y0, 1 plus y0. If y0 goes way, way up, the reflectance goes to infinity. That's the zone of high reflectance, okay? Now, this is the point that the determinant of 1 is 1. So this is true. So E is the square root of M21 over M12. So it pops right out. And so we end up with M11 is not equal, if it's an unsymmetrical arrangement, I can't have M11 equal to M12. And it's also optical for a 5-layer. And now people, remember, we have limitations. Changes in angle cannot be estimated. Okay? So this is all done, all right, at small angle or 0. Okay? So we're flying blind when we're talking about a 45-degree beam splitter. Okay? So what do? We start with it, then we get on the computer and touch it up. Okay? Now we have one symmetrical period. What about the entire stack? Then this is the final. It's a single, so we have that we have S periods of the form PQQ. So this to the S is S gamma. So we have, this is the entire stack. All right. So let me show you what it looks like when you do it. And here, we're using two materials. This is lambda 0 over lambda. Okay. So this is the 1 stack here. This is the 3 at the edge, right? Remember? This is a 1, 3, 5 stack. So it's L on 2, H. It's either L on 2, H, L on 2, or H on 2, L, H on 2. Okay? This is called the stop band, which is that, well, if the equivalent optical admittance is 18 or 20, 1 minus E over 1 plus E, it's an enormous 99.999. Yeah, that's the reflectivity being 99.99. That's your laser mirror. This envelope here, for low, high, low, bounds between, means that the oscillation in here, if the index of the base material is 1.5 in here, then the oscillations are going to be between that and this. And then on coming down between this and that in this area. Okay? You follow? So isn't that terrific? In one shot, just by calculating LHL, you get this curve out. Now, this program, characteristic filter, open filters, doesn't have that, but other programs have a Herpin section in which you can put this together and ask it to give you the shape for various kernel designs. Okay? Now, here is the same thing for various values of the index. Now, I want you to look at this and you say, hey, wait a minute. I've got this, think of this as index of refraction. Ooh, isn't this interesting? If I take and look and work in the first quarter over here, okay, right, in this area, and I want to make an index between the 138 and the 175 or 2, all I have to do is put together one of these combinations so that I can put together any anti-reflection coating I want by making up a series of high-low oxides that I know very well. I don't have to go find parasodium oxide or cerium trifluoride, etc., with its index being 1,7. I can make 1,7 index by making a combination of titanium dioxide and SiO2 in the same machine. Now remember, optical coated material control is the name of the game, stoichiometry. And if you go into an optical coating house, you will see all the coating machines in the visible section have only 2 materials in them, SiO2 and TiO2. Why? We know these materials, they're hard, they're glassy, they don't produce problems, and they make very good glassy-like films. So if you go to this company and say, hey, I want to make an index to anti-reflect some material and I want to use triethyl methyl so-and-so at an index of 1.23 or 124, he says, I can't put that in my machines because you'll poison that machine because it's set up to do oxides and he won't change it. He says, but what I'll do is I'll synthesize that index for you using the two materials that are in this machine. And that's how it's done. So you can see how it's done here. Now, let's go back now to the oscillation problem, okay? Okay, that's occurring in the stack. Now, here is the problem. This is the reflectance. Here is the envelope. RE is the index of the whole film. That's this envelope, okay? And this is the line here, all right, which is the substrate. And so the envelope, the actual reflections, is going to oscillate in that, okay? This one is the wrong one for that. Let's go back. Let's show you that in a minute. File. You got to close the project. File. Let's go to the original stack, okay, and analyze reflectance at 0. Yes. So this is the envelope of this one. Okay. This is the classic quarter wave stack, and it oscillates between the reflectance down here, which is the substrate, which is this line over here. Okay. And this, so that what we want to do is we want to make these go away and have this come up. We want this to be our passband. We want to get the oscillations down. We want the leakage. They used to call it leakage. Leakage to go to 0. All right. So what we're going to do is what Epstein did was say, hey, you know, and we got these discussions. So we have this envelope has a certain index, Herpin index, and the air has a certain index. So let us add a multi-layer, an E to the front of it to balance it out. And so we can figure out what we want. We want to reduce the ripple of the filter due to the mismatch of admittances between substrate, multi-layer, and the medium. So we're going to anti-reflect the multi-layer. All right. And so we take this, and now this looks familiar. Remember what happens when we have an index of 4 to air? Well, what would the index of the anti-reflecting film be? Square root of N0 and substrate. That would be the square root of 1 times 4, the square root of 4, which is material of 2. Well, we can do that at any intersection. So here I have this index. I want the square root of the material, NE, and N1 should be the square root of N0 times E. That's the Strong's condition, the square root of the material. So here we have N0, the air. Here's the E, which is this 20-layer stack. We're dealing with it as it's one layer of Herpin index E, okay? And we want to couple it to the air, and we want to couple it, anti-reflect this to this, okay? Just like we match a single film. And so we put it in, here it is, we plot E for 2, this is a case of high index glass on germanium. And look at the region where we're going to from 1 to 2 in G, lambda 0 over lu. This is 1. So we're in the 2 region, okay? This is the E, and then here's the reflectance at the same point. Here's the uncoated germanium. Now we add to this a little bit of a coating. This is the substrate, and we AR coated substrate, and we bring a large reduction down in the band pass ripple. Okay, and this is how we shipped the cameras out of England and gave them to the Russians, and they put them together, and then we left them because then I think we boycotted the Olympics, as I remember it. So we put these coatings put the Russians into color TV. All right. So now let's look at well, it's 7:10. We should take a break. Let's look here at this is almost a quarter wave stack. Let's look at the modified Lambda quarter wave stack. Okay, so file, close the project, and file number 3, 21 layers, and analyze, calculate the reflectance. Okay, so now we have a stack which has been modified to reflect the blue, shortly come down and transmit. Well, you can also do this the other way. Analyze, calculate the transmission. Okay, so there's the transmission of the filter. It will transmit from 450 all the way out to 700 pretty nicely. Okay, but what's most important is that the Wiggles in the 400 to 450 region, which is the blue, are very, very little. Right? Right? So that is how we took care of this problem. Right? Now, what we did was we moved the lambda 0 to 400 project add filter. Yeah, we are at 550 wavelengths from 300 to 1,000. Okay, and what was this? Oh, I don't know what this was. Number of front layers. Oh, this is the back layer. Did I modify that? Front layers, back layers 1. I made a mistake. You got to be careful when you go to project and you say add a filter. You said consider the backside, which is the other side of this thickness of glass. He's using this program to design real materials which have 2 sides to them and a coating on both sides. This is the backside coating. So if you don't consider the backside, turn this off, okay, then you're only looking at the front coating from 550 to 1,000, okay? And for some reason, remove this one and remove this one. Okay, so there's our coating. Now, as we tilt this coating, hell breaks out to some degree. Analyze, calculate the transmission now as we go to, let's say, 45 degrees and unpolarized, meaning we'll do both sides. Okay, so you notice it's shifted and there's a little hitch in here. We've got the suppression here, but this causes some problem between the 45-degree transmission and this one. So what we ended up doing, if you look at the cameras, instead of coming in and splitting the beams at 45 degrees, we would go and say, take this and say, no, let's give it, analyze, calculate transmission, and they would go to 30 degrees, okay, unpolarized. Okay, so there you see what we had. At 30 degrees, we got rid of this hitch right in the middle. All right, so let's remove all the curves and then analyze, calculate the transmission at 30 degrees, unpolarized. Okay, so now you see this is the filter. When you look inside a very good color TV camera, they will have a color prism in it, and it will have these reflecting films in it, but the film will be at 30 degrees. Each red, green, and blue camera inside will be at 30 degrees to the beam so that we don't get into a problem of this transmission. Okay. Okay. Automatic vision 1-to-1. Okay. So much for this. And it's 7 o'clock. Question, people, did I go through this too fast? Nobody's answering.
I'm following.
Oh, good.
So if I could follow, your students should have no problem with this.
Oh, okay. Okay. That makes me
Think
feel
you're doing
better.
all right, Professor.
Huh?
Think you're doing all right, Professor. Yeah.
Okay, I hope so. Gonna understand that this stuff is like all of the good stuff ferreted away in the papers, and it's very rare that a person who hasn't worked in the industry would even come up against it. All right. I do consult for a very large optical coating company called Spectrum Thin Films out on Long Island, and they also have people trained in design. And I ended up showing them these techniques. They are very good at open filters or a similar program. They'll do it a different way, which I will show you. Okay. Now let me go to the.
I thought you were going to take a break.
Yeah, that's I think what we're going to do, and I want to go to the next thing is this one, which is the Herpin index, the burning approximation, which is the second most important use of the Herpin index, which is how do you make everything out of two other indices that you know about? This burning approximation. All right. Now, Burning was an early guy at the U.S. Naval Laboratories, and he was an optical man. And he was also dealing, the Navy does a lot of work in optics. The Naval Research Center has been known for that. And China Lake out at the Michelson Lab out in California, which I was at, also had done some phenomenal work in anti-reflection coatings and visibility and atmospherics and all of that. Now, what we have here, he says, look, I've got 138 and 230. There's a reason for that. This is early in the games, and they just barely could produce TiO2 from an electron beam gun. So mag fluoride, of course, is a crystal evaporated from a crucible. It's easy enough to do, but he's got these two indexes, 138 and 230. And his problem is he really wants to go to match this to the air. Okay. And he wants symmetrical multi-layers with constant thickness. So the E, the admittance, is between the high and the low index. So we should be able to find any index we want between 138 and 2.30 in a form. Okay. So E is equal to this at 0. So we want 17828. So we take gamma two periods of 1 and 1 period in the middle, and the ratio is this, and he works out that the E is approximately this, and the gamma, the phase, is approximately this. All right. You know he's going to put this into the computer and play with it and optimize it later. So what he did was he wants he wants a quarter wave thickness or 270. So he's selected phi1 is equal to phi2 on 2e8 quarter eighth. All right. Looking at the phi and the psi, we get 1 and 2 phi, and take N1 is 1.35 and N2 is 4. So he wants the AR coat germanium. All right. All right. And he doesn't have index 2. So here is the selection we have for the various values. We can select any ratio of psi to produce an index from 1, 2.58 all the way up to 2.75.
So you're
on this plot.
synthesizing.
Yes, we're synthesizing that layer. So plot LHL for one, and one gets the various ratios, and then plot HLL, and we see its index is also between 0.5 and 5. Okay, so that we have a set established. So a symmetrical three-layer combination behaves like a homogeneous single film of low dispersion whose famous phase thickness is approximately 2 times phi1 plus phi2, which is, in our case, 1/8 quarter eighth, okay? Now, any multiple of periods can also have the same E, but the phase thickness is now M gamma. So here he says, procedure, we can construct an equivalent layer using this being the index, choose gamma to be an integral division. We solve the formula for gamma. So now here is an example. All right, so we have a low index of 135 and a high of 4. So this is NH air 1.5. Single layer on this, on glass 1.5 high air. Replace the 2.32 by a 3-layer period. Now, now look, this is glass. I'm putting on 2.32 index. So what am I going to get? I'm going to get a reflection increasing film. This is a beam splitter. Okay? I expect the reflectivity to be higher because the index is higher than the glass. And it's a single layer film. So we pick at 0, psi is equal to 1, NE is 2.32, so psi is 2 phi2 over, so phi1 is phi2 over 2. We want a 90 degrees, so let's pick 4 repeats of this to make a quarter wave layer, all right? 4 times, so we got 4 times 22.5 degrees. The layer is gonna be 90 divided by 4, right? 4 periods of layer. So that's 22.5 degrees. Solving for gamma, we end up that gamma is 19.5 degrees is equal to 2 phi1 plus phi2. 2 phi1 is phi2. So phi2 is 9.75 degrees. Phi1 is 4.88 degrees. And so that means that phi is FR times G. Said G is equal to 1. You got FR is 0.1083 quarters, and the other one is 0.054 quarters. So the equivalent film is 0.054 low, 0.1083 high, 0.054 low 4 times, okay? And if we put that in, here is the single layer film, and here's the equivalent, all right? And we check 5454 plus is 0.216, all right, is the check, okay? So we've produced from a low and a high, an intermediate index high film, right? The other example is our famous quarter or our for the coating on germanium, all right, germanium or glass. What is it? Was it NH? Did I put it as high as 2.96? Medium is 2, 4, germanium. So germanium is index of 4 in the infrared. So we want a step down coating for 2.96 to 1.35. The problem is 2 is easy. 135 is easy. 296 is a pain. Okay? So we want 2.96 using only 135 and 4. So using HLH, that's 4, 135, and 4. Because, of course, look, the H next to the germanium doesn't exist and gets 1 less layer. In other words, if I take this and I make this a high, low, high again, the high will make this layer thicker and it'll coalesce into 1 layer, right? I'll have 1 less layer. So I'm saying I'm projecting 3 layers, 5 layers, so it'll drop down to 1 less layer. 1, 2, 3, 4, 5, rather than 3, 3, right, right. So this would be high, a fraction high, low, high, low. Okay, the fraction high and the high will coalesce into one. So let's see what happens. We take the index as 2. We look at the formula. It's approximately this. So psi is 2.84. That's 2 phi over phi1. Working the formula out, phi1 is 1.420 phi2. Now the thing is, how many periods do we want to do? Let's do 2 periods. Assumption, first time through. Most people don't even do that. They just put fractions in and they let the machine optimize it. All right. And I'll probably do that next week to see, get you used to the optimization of these things. All right. In the design optimized portion of this. It's not critical for your base education in optical thin films because most of the time you're going to be specifying designs requirements, and no matter what, if you made up an equivalent preliminary design, the gain you would have is that it would certainly put you ahead of other people on the input basket to the design people at a thin film house. They would say, oh, here's a preliminary design. Can you make this versus, can you give me this kind of reflectance? So and so. And he has to work out what structures could possibly do it for him. Whereas you would be giving him a guided introduction to what you wanted. It doesn't happen too often, but if they know you're a thin film person, you can talk to them about the trade-off in the design better than a person who doesn't have the intimate details as to the product performance that you would have. All right. Now, also, you're going to be involved in every crazy thing in the world in terms of thin films, including matching crazy crystals at strange angles, etc. And so this is going to give you some idea that, can it be done? Can I make a cavity in this material to produce UV light of a certain intensity? How do the mirrors have to be reflective, given that the material has a very strange index and it's electro-optical? All of these things are in your future, okay? All right, now, so we made an assumption. I said, let's do this twice. So gamma is 2 phi 1, so gamma is this, and we end up with rho is 40.243 degrees is equal to 2 phi 1 plus phi 2. So phi 1 is this. 40 degrees works out to be twice 1.42 plus phi 2. Phi 1 is 14 degrees. Delta is then 0.165. And phi 2 is 10.4 degrees. So delta is 0.116. So we have this. We have 0.65H, 0.116L, 0.165H twice. How about getting rid of the index of 2? So this is the middle one. The middle index, we can make up the same way, and we find out we have O8H, 28L, OHH. This is just arithmetic, all right? And so out comes this design, all right? Now, when you look at this, we expand it. Now, this doesn't exist. There's no change in index. So this gets absorbed into the germanium. This and this are the same height. So this compresses. These two compress. These two compress. So we have 2 materials and 9 layers. 11633, 116, 245, 268, 116, 168, 268 L air. All right. So we have a final pre-optimized design. Results in 2 materials and 9 layers. The results are superior. And here we have a BBAR coating for the 3 to 9 micron region, in which the coating is less than 2% over the entire region. Okay. You can get less dispersion and even closer agreement, but with 17 layers. All right. So in doing this stuff, what does is say, well, what I really want to know is just give me a calculation of the Erpin index and the calculation for various materials. Here I have a program written. I don't even think it's in MATLAB. I think this is in CAD, not a CAD program, MathCAD, not MATLAB. CAD program in which I just evaluate H onto L, H onto, produce the final M, and from that, this over this is Q. E is the square root of Q sub G, okay? And P is the number of periods, so the signal is H to the P, 1 over A to N. That's the reflection, okay? YG is this, NG is this. And so one plots it for these things, and there we have the 1, 3, 5, 7 stack. Here is the equivalent index, okay? This, remember, the oscillation is between the substrate, which is 155 down here, okay, in here, 155. So this is going to have the oscillations here. This envelope is holding this. This envelope is holding this. This is the high reflection stack, okay? This is the 3, the 5, the 7, the 9. All of this, of course, if you're in the first stack at G is equal to G of lambda is 1, all of this is all to the blue side in the spectral curve, okay? All right? All right. Now, just take a break from this. All right. And let me look now at 2173. Where is it? It's 2173 and 2174. This is the Mill Handbook, of course. Okay, 21. Come on, 21. Ooh. 20, that's interference filters. 21, 2173. Oh, wrong one. 2173. It's in here. Sorry about that. Why don't I drag this down? $21.73. All right. Here is the coding. Here's the coding, which is a standard stack with an eighth wave on each side. All right. Which is eighth, high, low, high, low, high, low, high, low, high, low, eighth. Okay. It's high, low to the fifth high. So this is your quarter wave stack. Remember, this is 0.75 on lambda, where lambda on lambda 0. This is G is equal to 1. So it's symmetrical around G is equal to 1. So this comes up and wiggles evenly. So this is the wavelength, but only on one side. All right. So on the short side. And he's using index of 235 and 138 on glass at 1.52. That's mag fluoride and titanium dioxide on glass. The reason we do not do this, that is, we don't use 138, is that the magnesium fluoride has high tensile stress. And when you coat it on a material like 2.35, it tends to crack, break up. I'll bring in the thin film in the laboratory, in the optical laboratory. I'll show you examples of these things. So we replace this N1.38 magnesium fluoride with quartz SiO2, which has a lower stress factor, and the stress relief between the high and the low lets the film stay in one piece. Stress relief in films is a high problem with the materials involved. Okay. Now, this is the beginning part of it. This is high, low, high. And now he says he comes along, he adds an eighth wave on either side. So he writes it 0.5 high, 0.5 low to the sixth period. Okay. With the multi-layer. All right, which has been added each of an automata of low index refractive index of optical path, 6 repeated tri-layers, or L on 2, H, L on 2. So this is what started the whole business of the equivalent layers. And here's the answer for it afterwards. You notice the oscillations have been reduced, okay, because of the half wave layer, okay? What you're looking at is the other side of this, essentially, okay? He didn't go down low enough to show you this point, right? So now this is, now let me say one more thing to you. This is a Fabry-Perot. This is the next subject area I want to talk to you before we quit for the day, which is 14 minutes. You all know about the Fabry-Perot interferometer. That's 2 mirrors, a mirror, and a spacer between them, right? And this is a mirror, which is high, low, high, low, high, low. Here is a spacer, which is LL, high, low, high, low, high, low. So if you put this together, does he have it in 21? No, he may have had it. Let's come over here, file, close project. No, file, new project. And of course, what you have to do is go to materials, manage the materials, make sure you've got what you want in there. So let's do it again, SiO2, high and low, okay? Actually, yeah, SiO2 and high and low, okay? Close that. And then project,
You
add a
didn't do
filter.
anything.
I know, I just check. No, it's strange. If you don't go to the materials handbook, sometimes it can't find it.
But I thought the thing said you had to gray it out to do something with it.
Yeah, no, I know what it is. I just use the same materials. You have to go to the materials catalog somehow. Maybe I'm wrong, but I've had problems with the program this way. So I got this, and I want to filter reference of 550, and I want to go wavelengths from, not 550, I want to go from 500 to 600. Okay. Don't consider the backside. Okay. And you have to do that first. So now, filter stack formula. Now, let's go ahead, high material, TiO2. And now low, and SiO2. Okay,
Yeah,
I don't know why that
flaky.
happens. Stack
Flaky.
formula. So let us make a mirror. LH, 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 and now we're going to make a half wave middle, LL, then HL, 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 HL. Okay? So here is our spacer, the LL spacer. We have a mirror on this side and a mirror on that side. nicely parallel, okay. And now I say, and analyze, calculate the transmission at 0. And there is our filter, okay? Okay, and that means that we have a filter which has a pass band here. This is 540 to 560 of, oh, well, what do you want to call it? At the halfway point? At the halfway point, we go from here, which is about 545 to 555. So this is about 110 nanometer, no, 100 nanometer band pass. Okay, this is the Fabry-Perot interference filter. Now, you'll notice that this filter looks great this way. All right, let's do the following. Okay, let's look at where it doesn't reflect. This is the transmission. Okay, now if I change the properties, okay, from 500 to 600, let's go from 400 to 800 and see what happens. Okay. Oh, it didn't trace it. Analyze, calculate the reflection. Okay. Okay. Well, let's remove all the curves and let's say filter properties, and we're going 500 to 600. Let's go from 400 to 800. Okay, and we say okay, and now we say analyze, calculate the transmission again. So now you see the filter, and you see what we have, which is the major problem of interference filters, is that I can give you a very sharp 550 transmission, but we have to block out a tremendous amount where the multiple interference doesn't work off the wavelength. So the first thing I have to do is get rid of the ultraviolet, the blue part. So what we typically buy is a glass which is made of absorptive materials, a base material. And that base material will come in here and we'll have a drop like so. So we'll eliminate all of the wavelengths below 500 to 400 or below. So that'll do that. The next thing is more difficult, which is the infrared, the red blocking filter. The blocking of this part of this business is intensively different. It is a metal dielectric filter, which has the transmission properties of passing like a big broad thing like so, which we would center on this, and it would eliminate the red portion of the spectrum. That's called the blocking. So a filter, an interference filter, which you're going to be using for your selective experiments, has a doubled specification all the time. The first thing, of course, is the transmission and the bandwidth that you want, all right, in the wavelength of the filter. The second, and probably the most difficult part of it, is what is the blocking? And they usually specify things like, well, the blocking here, the blocking at the low side would be less than 4 OD, density of 4, which is the log of the transmission, okay? 4 is 0.0001. The blocking from 400 to 500 is density 4, and the blocking from 600 to a micron is density 6, all right? So that you would know how much of this noise is getting into your experiment. So just to repeat this as my finalization here is, I'm going to go back to, let me see if I can find what I want, various interference filters. Obviously, the MIL 141 is not made to be a consecutive teacher, but rather as a encyclopedia of design types, all right, without making a selection as to one or the other. I'm looking for the interference filter pictures. Bear with me, and then we will go over this again Wednesday to give you a feeling for the filters that you're going to be specifying and what their problems can be. This is microscope optics, and I think that's it for. Okay, so I got to go to the other Mill 41 Part 4. Yes, all right. And we'll finish up with that. Yeah, here's filters. Okay. Now, here are various types of bandpass filters. Is this subject important? Oh, God. This is various filters. We go over the resolving power of a Fabry Pro interferometer, okay? And we talk about the Q, and the classical Fabry Pro is two mirrors and two glasses with a gap between them. We then replace this gap with a piezoelectric crystal so that the gap can be scanned back and forth, and we have a scanning Fabry Pro interferometer in the lab, which is used to scan across a wavelength line and present it on the scope so you can actually see the laser line shape on the oscilloscope. We all do this as a standard project, a standard experiment that we do in the advanced optics lab. Now, what else we do with this is if we scan this and differentiate it, then we can lock the experiment that we're doing onto the laser line. So we have a phase lock laser line or a phase lock wavelength, so we can do optically pump atoms up and down at the exact wavelength that they need. So the Fabry Pro interferometers are used all over the place for atomic quantum optical experiments, in which we have to be at that energy and hold that energy very, very carefully to cool the atoms. Okay, with me? We'll go through that later on. So here's multi-layer film, and again, we have a layer and a spacer, and these are the various available filters from various manufacturers way back when. Some of these companies no longer even in business anymore. Remember, this was written in 1952. All right. Now, the wavelength, the transmission in the passband, the width of the band, and the extent of attenuation. The shift of transmission is a function of the angle of incidence. So bandpass filters containing metals. So here is a filter, and you'll notice the long wavelength problems, all right, involved in the filter, all right, and then they have double line filters. So here's an all electric Fabry Perot. High, low, low is the half wave spacer. High, low, high. And the concept of the transmission is we can coalesce it to find out what the transmission is. At lambda 0, this is a half wave, this appears, then this disappears. So this LL is a half wave with HH. So the transmission of the filter is glass to air. So it should be about 93%, all right? Because it's only the reflection of the glass to the air left at lambda 0. Again, if you're at lambda 0 and you have this thing, you can coalesce everything together. LL is a half wave. It doesn't exist at lambda 0. Then you had HH, which coalesces. Then LL again, then HH. So you end up with at lambda 0, glass air. So the reflection in glass air should be square root, the reflectivity should be about 1.5%. So you should be about 99% transmission, okay? And here you have this Fabry Perot, all right? And here you see this is the passband of it. And if you look at this closely, low, high, we have this sort of bandpass here, rather broad, okay? He doesn't show you outside of here this stuff and this stuff, which is you a problem. Now, if he get 2-layer filters, we can end up with here. This is the first film is 1 high. This one is a half, and another half. Number 2. Number 3 is LL high, low, LL high, so that it is a better pass band than this. You want this pass band rather than this singular pass band. You want a broader transmission over the wavelength region involved. Okay, so this is a double half wave coding. High, low, high, low, high. So here is a half wave, and here is a half wave. All right. So if I go to that, I'm not going to do that now. It's 8 o'clock. I've talked myself pretty much out. Here is a composite filter, 11-layer bandpass filter with an 11-layer long pass filter blocking on arsenic trisulfide glass. So the composite is here on the glass, okay? And here is the pass band, and this is the other layer of the other coating, which comes up at 10 microns. So we have this giving us, so we end up with almost nothing, this and this between 2 and 9 with a little bit of leakage at 10, okay? So it's a composite filter, band pass and long pass on glass to kill the blue. Now we can get very, very narrow coatings as well. And it is so sensitive that if you start moving the filter around by twisting it, it shifts the peak, okay? So here's a 7-layer bandpass filter, all right, at 10 microns in the infrared, all right? And here you see the outside bands of a Fabre-Perot, which is one layer of high and low material, all right? This is what you would typically see as your spectral reduction, all right? So he's saying to you that there's the filter spec, and I'm going to stop, and we'll go over this again, all right, is that the transmission is 0.65, in this case 2.7. The bandwidth at half power is 0.12 microns. Right. The transmission below 2.5 microns, the transmission is less than 0.001, and the transmission above 2.9 micron is less than 0.01. That's in this area. And that's the bandpass filter specification that you should know about. All right. This is what you have to spec this for any filter, all right, in the experiments that you get. Now, when you get into those laboratories, you're going to be seeing filters thrown about, bandied about. Remember that they all have this specification, and some of them leak in the blue, they leak in the red, and they will produce all kinds of problems to you. And if you have them and you start twisting them in their mounts, you will shift things around a bit. All right. And that is where I will stop for the night.